Hello everybody. So in this video we are going to solve an example on the recycle and the splitter. And this is going to be a good example to include both of them in the same problem. Um, we said before that the recycle is mainly used in the cases of reactions for incomplete reactions, but since we haven't covered this reaction calculations in mass balance, we are going to do this for another system. However, the concept is the same, so it's going to work, inshallah. So what we have here is an air conditioning system. We have fresh air that contains 4 more percent water vapor, and it's desired to dehumidify this air to water content of 1.7, meaning that we want to reduce the water vapor content in the air. And we are told that a stream of fresh air is combined with a recycled stream from previously dehumidified air passed through the dehumidifier. So one thing that we have to keep in mind in cases of flow sheets including recycled streams is that you have to deal with information from the far end of the end of the process to deal with this information in the beginning of the process. So for now you don't have to know exactly where this stream is coming from. You just know that there is a recycled stream that comes from the front, and it's mixed with the fresh air that is coming from the very beginning of the process. So for now, in the time being, we know that there is a recycled stream that comes and is combined with the fresh air, and that the blended stream, which is the mixed feed, is entering the dehumidifier, and it contains 2.3 mole percent water. And the dehumidifier is just an air conditioner. It reduces the temperature of air, so water condenses and the water content in the air is reduced. So this is what happens, and it says that water condensed and removed as liquid, and the dehumidified air that comes from the dehumidifier is split into two parts. Part of them, a fraction, is recycled, which is the same stream that we were discussing at the beginning, and the remainder is delivered to the room. We will take 100 moles of dehumidified air as a basis, and we need to calculate the rest of the flow rates. So we agreed that the first step we have to follow is to draw the flow sheet, and this is what we are going to do now. And there is something we need to do after drawing the flow sheet, is to double check and read again the flow sheet and make sure that everything fits with the diagram that we have. So we have 4 mole percent water vapor airstream. Yeah, the airstream contains 4% water vapor, and it's combined with the recycled stream. So this stream 6 is the recycled stream. This is where they are combined, and the blended stream, which is stream number 2, is fed to the dehumidifier. It contains 2.3 mole percent water vapor, and some of water is condensed, which is stream 3, and removed as liquid. Then we have, it's just liquid water, so we have no other components. For stream 4, this is the dehumidified air, and part of it is recycled, and the rest is delivered to the room. We know that the flow rate is 100 mole of dehumidified air, and we know that this is 1.7%, which is the desired water vapor content in the product stream. So this is a good thing to do, to make sure that the flow sheet is really describing the process in the text. Especially that you're not going to refer to the text anymore. We are going to deal with the flow sheet. So if there is something wrong with the flow sheet, then the rest of the solution is going to be wrong. So we have to first, after doing or drawing the flow sheet, we have to do the degrees of freedom analysis. And in the degrees of freedom analysis, we can do this for each one of the units and to the overall loop. So if we do this for the mixer, we have 6 variables, 2, 2, 2. So we have 6 variables. We have two given information, two given independent information, so one here and one here, and we have two equations, and because we have two components and we have no relation, so this will give us 2 degrees of freedom. For the dehumidifier, we have 2, 4, 5. We have 5 variables. We know one independent variable. This is not given variable or an independent variable, it's dependent. So we have one given variable. We have two equations, so and no relation, so this makes the degrees of freedom equal 2. Now for the splitter, we have 1, 2, 3, 4, 5, 6 variables. We have two given variables. We have two equations, and for the additional relation we will add the splitter restriction. It's number of splits minus 1, which is 2 splits minus 1 times the number of components, which is 2 minus 1 as well. So this is going to be 1. Again, we can to just confirm what we mentioned in the previous video, we can put the compositions, and if we put the compositions in the 3 streams, we will have one more information here and one more information here, so this will make the number of given variables 2, but we have to put the number of equations equal to 1. So this is going to be 6 minus 4 minus 1, which is the same output. Because the splitter is not solvable with the given information, so we cannot solve it. Now for the overall, we are looking at streams 1, 3, and 5. Stream 6 is not considered because it's like 4 and 2. It's a stream going from one unit to another unit. It's not going outside the process or inside the process. It's from unit to the unit. So we have 1, 2, 3, 4, 5 components. We have 1, 2, 3 given variables. And 2 equations, and this makes the degrees of freedom equal to 0. So now the steps of the solution would be first solving the overall loop, and by solving the overall loop we will have one information given to the mixer, one information given to the dehumidifier. But this is not going to be enough because we have 2 and 2. So the mixer cannot be solved and the dehumidifier cannot be solved. But there is one trick that we can play, which is using the relation that we know about the splitter, which is the composition of stream 5 equals that of 4 and of 6. So we can use these compositions in stream 4 and 6. Again, we didn't do this in the beginning because we were just doing the degrees of freedom analysis. Once we do the solution, we have to use this relation. So we are using this relation by putting the information here. So we will add one more information to the dehumidifier, one information to the mixer, so we can solve the mixer and the dehumidifier. So we'll start with the overall loop, then the mixer, and then we can solve the dehumidifier or the splitter. So this is the plan that we're going to follow. So for the overall loop, we have let's go back to the table. We have 2 equations, and we have 5 minus 3. We have 2 unknown variables, which are n1 and n3. So we want to calculate n1 and n3. We have 3 equations, and we need to pick 2 of them. The 3 equations are the total balance, balance on water, and balance on A. For the total balance, we have n1, n2, and n3, so n5 and n3. So n1 and n3 are unknowns. So we have two unknowns in one equation. We cannot calculate them directly. For water, we have water here, water here, water here. So again, we have two variables in one equation. So if we use these 2 equations for the total and water, we will have 2 equations and 2 unknowns, which is not a big deal. But if we apply, look at the air, we have air here only and only here. So it's going to be 1 equation and 1 unknown. So you can calculate n1 directly by applying the balance on A, and then you can apply the total balance to get n3. So this is going to be easier. And instead of solving 2 equations and 2 unknowns, you can solve 1 equation and 1 unknown, which is much easier, and it will reduce the probability of doing mistakes in the calculations. So for the overall loop, we will start with the balance on air. It's going to be air in equals air out. It's as simple as this. We can calculate n1 and from the total balance is going to be a piece of cake. And for now we have 102.4 equals 100 plus N3, so N3 is 2.4. It's not even it doesn't even need to be calculated. It's by just looking at the numbers you will find this out. Now we will update the degrees of freedom table according to the plan that we mentioned. So here I put the flow rates of N1 and N2, and here we have the compositions that I mentioned before. I put the compositions in the 3 streams. The overall is done. Okay, we have no updates for the overall, so we can add to the mixer one information, which is N1, and one extra information, which is the composition in stream 6. The same for the dehumidifier. We will add one information, which is N3, which we got from the overall, and one extra information, which is the composition in stream 4. So this makes them both solvable. For the splitter, the degrees of freedom is not affected because we haven't done anything extra for the splitter. We haven't got any extra information for the splitter. So what we have here is just rearranging the information. So now when we do the degrees of freedom, if you want to change the degrees of freedom to include this information, so you have 6 variables, you have 4 given variables, 2, 3, and 4 given variables, and 1 equation. So it's still 1. Splitter is not solvable with the given information till now. So for the mixer is going to be easy. You just need to write 2 equations and 2 unknowns. So you will write the balance on air. There is no other option. We have to solve 2 equations, 2 unknowns. So we have balance on air, so it's air in stream 1 plus air in stream 6 equals air in stream 2. By substitution, we have 2 equations, 2 variables, and the total balance is N1 plus N6 equals N2. So now we can solve the 2 equations simultaneously to get the value of N2 and N6. And of course, if you know N6, N5, the equation of a splitter is going to be very straightforward. 290 plus 100, this is going to be 390.1. So I didn't do this because it's very straightforward. So this is the final flow sheet after putting all the information and all the compositions. So by doing this, we are done with the mass balance for non-reactive systems, for multi-unit non-reactive systems. Starting the next video, we will start a new topic, which is a very important topic, which is the mass balance on reactive systems. You will see if we have a reaction or a reactor, how can we include the reactions, and we can include the terms for generation and consumption that we mentioned in the beginning of this chapter. So we'll see you next time, inshallah. Goodbye.